Welcome back, dear children. Today we will be continuing solids and semiconductor materials. Chapter 12 of CBSE textbook. Lesson number 3. In the previous class, we have discussed about the classification of semiconductors as intrinsic and extrinsic semiconductor. And we stopped till intrinsic semiconductor. Today, we will learn about extrinsic semiconductor. You know, the conductivity of intrinsic semiconductor is very small. Their conductivity can be increased by adding suitable impurities to the crystal, pure semiconductor crystal. This process is known as doping. Such doped semiconductors are called extrinsic semiconductors. So we are adding impurity to the intrinsic semiconductors, but impurities are added in parts per million. And based on the nature of the impurity added, we can classify extrinsic semiconductors into two categories. First is known as N-type semiconductor and other is known as P-type semiconductor. So we will discuss further these N-type and P-type semiconductors. So we know what is doping. Doping is the process of adding impurities to the pure semiconductor to increase the conductivity. Based on the nature of the impurity added, we are classifying extrinsic semiconductors into two categories. One is N-type semiconductor, two is P-type semiconductor. In N-type semiconductor, we add a pentavalent impurity to the crystal structure. For N-type semiconductor, we add a pentavalent impurity to the crystal structure. So dopant, the impurity is known as dopant. Dopant atom is pentavalent. Pentavalent atom example, arsenic, antimony. These are two examples I am giving for pentavalent impurity. And you know, silicon, pure semiconductor. When we add this pentavalent impurity to silicon crystal, what is happening? We will see. And you all know silicon has 4 valence electrons. Valency is 4. So when pentavalent impurity is added, the pentavalent impurity forms covalent bond with the 4 silicon atoms. Like this. And 5th electron of the impurity become free. You know, in pure semiconductor, electrons and holes are generated thermally also. So these are additional electrons. So there will be large number of electrons in N-type semiconductor compared to the holes. Electrons are called majority carriers because they are more. Holes are called minority carriers. Okay. So how will you get an N-type semiconductor? If the pure semiconductor is doped with a pentavalent impurity. The 4 valence electrons of the pentavalent impurity form covalent bond with the 4 valence electrons of 4 neighboring silicon atoms. 5th electron become free. Okay. In addition to these electrons, electrons and holes are generated thermally. So number of electrons will be very, very large compared to the number of holes. Number of holes. Electrons are called majority carriers. Holes are called minority carriers. The 5 valence electrons of the pentavalent impurity forms covalent bond with 4 the 5th electron becomes free. In addition to such electrons, electrons and holes are generated thermally. So, in N-type semiconductor, number of electrons will be very large compared to number of holes. Electrons are called majority carriers, holes are called minority carriers. If number of electrons per unit volume is denoted by Ne and number of holes per unit volume is represented by NH, then we can say Ne very much greater than NH. What is this Ne? Ne is number of electrons per unit volume. NH number of holes per unit volume. Electrons are called majority carriers. Holes are minority carriers. It can be proved that Ne into NH, if you find the product of these two type of charge carriers, that will be equal to Na square. Na into NH nearly equal to Na square. This Na is known as intrinsic charge carriers. Intrinsic charge carrier concentration. This we have learned last class. Na is known as intrinsic charge carrier concentration. The impurity atom added is known as donor impurity. Why it is known as donor impurity? Because impurity atom donate electrons to the crystal structure. That is why it is known as donor impurity. And the electrons so created are called donor electrons. Donor impurity. The electrons so formed are called donor electrons. And these electrons have little less energy than conduction electrons. So these electrons form an energy level just below the conduction band. This energy level is known as donor energy level. Now I am going to draw the energy level diagram for N-type semiconductor. So the donor electrons have energy slightly less than the conduction electrons. You know, conduction electrons are free electrons. So these donor electrons form an energy just below the conduction band. This is the conduction band, CB. See, donor electrons form an energy level just behind it. This is called a donor energy level. Now I am drawing valence band down. So the energy gap is reduced. So conductivity is increased. Okay. Gap is reduced. So the conductivity is increased. So the golden points in this discussion are, first one is when pentavalent impurity is added to the pure semiconductor crystal, like germanium or silicon, we are getting N-type semiconductor. Second point is number density of electrons into number density of holes is equal to Ni square. Ni is known as intrinsic carrier concentration. The impurity atom is known as donor impurity as it donates electrons to the crystal structure. So what are the golden points? First one, dopant is pentavalent impurity. Second point, electrons are majority carriers. Holes are minority carriers. Third point is if you multiply Ne into NH, it will be nearly equal to Ni square. What is this Ni square? Ni is known as intrinsic carrier concentration. Another important point you have to remember is impurity atom donated electrons to the crystal structure. but crystal structure remains neutral. Why? When impurity atom donate one electron, the impurity the core become positive. So when atom gave one electron, the atom is the core that become positive. So charge is neutralized. Okay, that is the fourth point to remember. The crystal structure maintains charge neutrality. Why it is so? Because the number of additional charge carriers supplied by the impurity atom is equal to the ionized force in the lattice. Okay, when suppose I give an electron, I become positive. So positive electron charge, positive charge neutralize. Because the number of is equal to the number of ionized cores in the lattice. So this is about a P-type, N-type semiconductor. And we will discuss P-type semiconductor. In P-type semiconductor, the impurity added is trivalent impurity. If pure semiconductor is doped with the trivalent impurity, we get P-type semiconductor. P-type semiconductor. So here impurity added is trivalent impurity. Example of trivalent impurity. Example of trivalent impurity is boron, aluminum. So you have to add a trivalent impurity, bismuth. So I am adding a trivalent impurity. This is the trivalent impurity where valency is 3. So trivalent impurity make covalent bond with 3 silicon atoms. In the fourth bond, there is a vacancy. Vacancy of an electron, because impurity has only 3 atoms. In the fourth bond, there is a vacancy here. That vacancy is known as hole. This impurity is known as hole. So in P-type semiconductor, there will be very large number of holes. Very large number of holes. So due to the impurity atom, there is a hole. Electron and holes are generated thermally also. So large number of holes are there. Holes are called here majority carriers. Electrons are called minority carriers. So in p-type semiconductor, holes are the majority carriers, because holes number will be very large compared to the electrons. You know how electrons holes generated? Thermal agitation. Here holes, impurity produces additional holes. So number of holes are very large, number of holes is very large compared to the number of electrons. So NH will be very much greater than Ne. Holes are majority carriers. Electrons are minority carriers. And it can be shown that Ne into NH is nearly equal to Na square. Ne into NH nearly equal to Na square. You know, Na is intrinsic carrier concentration. Here also, after you are adding trivalent impurity, the crystal structure maintains charge neutrality, because number of additional charge carriers is equal to the ionized pores. The crystal structure maintains charge neutrality. And this impurities are called, this impurity is called acceptor impurity, because it accepts electrons from the crystal. Impurity is accepting electron from the crystal. The impurity is called acceptor impurity. Why it is called the acceptor impurity? Because it accepts, impurity accepts electron from the crystal. The holes form an energy level just above the valence band. The energy of such holes will be little more than the valence electrons. So they form an energy level just above the valence band. This energy level is known as acceptor energy level. So I am drawing the conduction band, valence band. The holes form an energy here. And this value is 0.01 electron volt to 0.05 electron volt. This is known as acceptor energy level. In the previous case also, donor energy level, its value is from 0.01 to 0.05 electron volt. So this is about intrinsic, this is about p-type semiconductor. So what are the important points to remember? This is called gold, such points are called golden points. First thing is, what are the points to be remembered? First one is impurity is trivalent. Second is holes are the majority carriers. Electrons are the minority carriers. Third point is Ne into NH nearly equal to Ni square. And crystal structure remains charge neutrality. First one is dopant is trivalent. Second point, holes are majority carriers. Majority carriers. Electrons, minority carriers. NH very much greater than Ne. Third point, Ne into NH nearly equal to Ni square. Fourth point, crystal structure maintains charge neutrality. Okay, dear children. So today we discussed about extrinsic semiconductors. Children, thank you for watching. We will continue in the next class.